In pretty much every single game that's ever been made, you have characters that need to travel from one location to another location. And in order to do that, they need to find a path. This is the basic problem of pathfinding. A world could be full of all sorts of obstacles, or could even be shaped like a gigantic maze. And your computer needs to quickly find a path around all of these obstacles, so that the characters know where to go. In video games, this is a tough problem because video games run in real time. That means you have to recalculate the entire game 60 times every second to create the illusion of a smooth video. And inside of each frame you have game logic and graphics and a bunch of other things as well. There often isn't very much budget left over for pathfinding. And this is a particularly big problem for the game that I'm making, because it's based around ants. Now in the Pikmin series, you have 100 little ant-like creatures that follow you around. But in my game, I want to have thousands of them. And that means you could have thousands of pathfinding requests triggering every single second. And this means, quite simply, that all of the off-the-shelf pathfinding solutions that you can find for the Unity engine were not good enough, and I've had to create my own unique solution. Well, I say unique, I didn't actually invent this approach. Instead, I've implemented it from this research paper called Crowd Pathfinding and Steering Using Flow Field Tiles. And this algorithm has been implemented before by other people. For example, I found this slideshow showing that it powered Age of Empires 4. And there's even some open source implementations of it up on the internet. But none of these implementations are for the Unity engine, which, let's be honest, that's what most game developers are using these days, me included. So I decided to bite the bullet and implement this extremely quick and powerful pathfinding algorithm for the Unity engine. In fact, I think it might just be the fastest pathfinding solution currently in existence for Unity engine, especially because I've used their data-oriented tech stack to create it. This is basically the high-performance mode of Unity, and I'm giving away the source code on my GitHub for all of you to try out yourself, if you want to. The algorithm is pretty sophisticated with a lot of moving parts and fiddly bells and whistles, and implementing it really pushed me to the edge of my programming skills. But the ideas behind it are fairly simple, so in this video I want to walk you through my journey of creating it. Let's start with a super quick history of pathfinding. It might surprise you to learn that pathfinding was actually solved all the way back in 1968 by a team of computer researchers. They created the A-star pathfinding algorithm, which is still the most commonly used algorithm to this very day. It's basically a perfect solution. Here's a quick intuitive understanding of how it works, skipping any of the overly mathematical details and stuff happening under the hood. Basically, the algorithm checks every single possible path between A and B, but it does this in the order of shortest to longest. This means that the first valid path we find must also therefore be the shortest valid path. It's a little bit more technical than that in the details, but the details don't matter for the purpose of this video. Now, the main downside of this algorithm is that it is still quite expensive. It has what we call a superlinear complexity, which means basically that if the size of the level doubles, then the time taken to pathfind through it will more than double. And in some cases it could be a lot more than double. And this is made worse by the fact that levels are two-dimensional. So if level 1 has a width and height of 10, level 2 has a width and height of 100, then you might expect that second level to be 10 times the size of the first one, because 100 is 10 times 10. But that's not the case. The level is actually 100 times larger, 10 squared. This means that pathfinding in level 2 could take more than 100 times longer than pathfinding inside level 1. So if you're making a game with big levels, then that is a crippling problem. So I said earlier that the A-star algorithm is basically perfect, at least in some sense, and it's still used to this day. But that doesn't mean that we can't improve on it. We absolutely can, using a trick in algorithm design that we call the space-time trade-off. In physics, people sometimes say that space and time are interconnected, like two sides of the same coin. Well, in computing this is also true, but in a completely different way and for completely unrelated reasons. Calculating things takes time. But if you calculate something and then you write down the result, the next time you're asked to calculate it, you can just give them the answer. It's the difference between working out a maths exercise in a classroom the proper way and just looking in the answer book. In other words, a computer can trade time for memory, or space as people often call it. And we're going to do that here. We're going to pre-compute a whole bunch of important facts about our level, so that when we've been asked to find a path, we basically have a cheat sheet of facts that can help us find that solution ultra fast. Now, if you've seen other pathfinding videos on YouTube, you might already be familiar with two common ways of doing this. The first is flow fields, and they're a really simple idea. Suppose we have lots of agents that all want to reach the same destination. Well, we could calculate all possible paths to that destination. That's going to take a while, but then we can store these paths as a flow field. You can imagine it as kind of being like a river. If the level is like a water basin or a river, and the destination is like a plug hole where the water is flowing out of the level, then this would create a current pushing every single location in the river towards that plug hole. And so to path find to this plug hole, all we have to do is follow the current. So calculating this flow field is expensive the first time around, but once it has been calculated, each agent can path find with approximately 0 effort. And so this scales really well if you have 100 enemies or 1,000 enemies that are all pathing to the same destination. For example, you might be playing a zombie apocalypse game where all of the zombies are trying to reach the player. Another major advantage of this algorithm is that it's very resilient. If the agent gets pushed off course by the wind or an explosion or being punched in the face by the player, then wherever they end up landing, they can still find a path to the destination for no extra cost. So if there's a lot of chaos in your game, this algorithm handles it very well. However, if you want to have your agents path find to many different destinations, then this approach falls apart because you'd have to create a whole new flow field for each of those destinations, and that gets very expensive very quickly. And this is also true if the level is changing, because every time it changes even slightly, you will have to recompute all of your flow fields. So flow fields have some major advantages, but they also have some big drawbacks. Let's look at a different approach. This is called hierarchical pathfinding. You won't find quite as many YouTube videos on this topic because, quite frankly, it's a much more complex algorithm, and therefore it's not as well suited to a video tutorial. But the idea behind it is, once again, very intuitive. Imagine you wanted to visit your friend who lives in a different city, and imagine you wanted to find your way there using an old-fashioned paper map, so no computer assistance. Now, these cities are quite far apart, and that means that there could be literally thousands of roads in between them, and therefore a brute force search of checking all of these roads would be very difficult. But of course, that's not what you'd do. Instead, you'd first look at the highways that connect the cities. That's because the fastest route between City A and City B is almost always going to use the highway system. Now, in the case of a video game, it's not going to be so conveniently divided into highways and minor roads. Instead, we're going to have to do that ourselves. And we do this by dividing the map into sections. So if you have a level of size 100, we might divide it into smaller sections of size 10. And as we talked about earlier, pathfinding on this smaller grid is more than 100 times faster than pathfinding on the big grid. So the time savings here can be enormous. And if the level happens to change, then we only have to recompute the area surrounding that change. The biggest downside of this approach is that we do have to find our way onto the highway network and also off the highway network at the end, slowing the algorithm down a bit. And the other downside is that it does not find perfect paths. Instead, it has a tendency to find nearly perfect paths, pretty good paths, but they'll be just a little bit longer and wigglier than they need to be. This is because the highway system is not going to be exact. Just like how in the real world, driving on the highway will often be a faster way to get to your destination, but it won't be the shortest way to get there. So let's now pause and think about both approaches. Flow fields give you instant pathfinding, and they are resilient to being interrupted and moved, and the paths are also easily shared between large numbers of agents. However, it's very slow to compute and to recompute these flow fields, and therefore it supports only one destination at a time, which is a huge weakness. On the other hand, hierarchical pathfinding is slower. It takes you longer to find paths, and it is quite brittle if you are interrupted or moved off the path. And it's also pretty hard to share paths between two agents. But on the plus side, it's very fast to recompute this network if the level changes, and it also supports many different destinations. The key insights to take from this is that the pros and cons of each algorithm are basically opposites. Each one covers the flaws of the other. So if we could combine them, then we could create an ultimate pathfinding algorithm that's good at everything. And that is the basic idea behind hierarchical flow fields, or flow tiles as they're being called in this research paper. Here's how it works. We start by building a normal hierarchical pathfinder. So we take a level such as this one and we divide it up into sectors. Then we take a look at the edges of each sector in turn, finding the openings that connect it to a neighboring sector. These openings are called portals by the research paper because they connect two points in space like a portal, I guess. Next, we have to divide these sectors up further into islands. An island is a connected area of space within the sector. So basically, if you imagine the black walls are like water, then the white tiles are like an archipelago of islands. And here I'm visualizing different islands as being different colors. Most of these sectors here only have one island, but some do have two. The next step is to combine the portals and the islands together. So each portal is then connected to each other portal in the same island, creating a graph that looks like this. This is our highway network. We then calculate the cost of traveling down each edge of the highway by using the A-star algorithm. These edges don't cross sector boundaries, which means the A-star pathfinding search also doesn't have to cross any sector boundaries. It can be done on the small grid, and that makes it much faster than checking the whole level. And once we've calculated these costs, we store them for future use. If the level happens to change at any time, then we only have to rebuild the area that has changed, specifically the sector containing those changes, and also any directly neighboring sectors will have to be recalculated as well. But even so, this does mean that most of the highway network remains intact anytime there's a change, and that's a big deal for big levels. So, we can now pathfind from one island to another island very fast and efficiently using this highway network. But we're not done yet. We have to find our way from each node in the highway path to the next one. And we have to find our way from the last node to our actual destination, which isn't actually part of the highway network. And we're going to do this using a large number of small flow fields. The generation of a flow field has exponential time complexity, meaning it's extremely important to keep them small, as smaller fields can be computed drastically faster than larger ones. And secondly, we don't actually have to compute fields for the entire level. We only have to compute them for the part of the level that we are pathing through. Specifically, each portal in our highway path will request the generation of one flow field, Plus we need an extra one for our starting point and one for our destination point. So if we have a highway path that is 10 portals long, then we will have to generate 12 of these small flow fields. Now generating these paths and flow fields is relatively fast because they are using small grids, as we've talked about, but they do still take a fair bit of time. So to speed this up further, we are going to store the results that we calculate in a big cache. Then any other agents that want to do a similar path can check the cache and use that shared data instead of having to calculate a new path from scratch. So a path can be shared if the start and destination cell are both the same. That's not always particularly common. However, in my ant game, this does happen a fair bit because the ants like to carry resources from point A to point B fairly often. But the flow fields can be shared whenever two agents in the same island are traveling to the same portal. And this happens all the time. If two agents are heading in even roughly the same direction, the chance of sharing their flow fields is high. But the downside of all of this is that when the level changes, large chunks of this cache do need to be cleared because it will no longer be valid information. So if the level is changing infrequently, like maybe once every handful of seconds, then this is not a big deal. But if the level is changing many times per second, then the algorithm will slow down drastically or may even fail to find paths at all. It needs a little bit of time after each level change to do this pre-computation. Now, I've been telling you all this time how fast this algorithm is, but words are cheap. Let's see this in action. This stress test example uses a 100 by 100 grid, meaning we've got roughly 10,000 agents here, and it's running at over 150 frames a second. And that's partly because my dev PC is quite beefy, but it's also because the algorithm is just extremely efficient. Most of the agents here can share their pathfinding data, so actually only a small minority of them are triggering new pathfinding requests on each frame, and over time, as more and more of these requests are cached, then the number of new pathfinding requests drops down to 0, meaning we have instantaneous pathfinding for all 10,000 agents. Now, of course, this is the best case scenario. Let's take a look at a more realistic scenario where the level is allowed to change. So here we have another 10,000 agents, but this time the level is being modified very rapidly, roughly 5 times a second, which is just about the absolute limit of how fast this algorithm can cope with being changed, at least on my PC. And this example is still running at over 150 frames a second. Every time the level changes, a lot of data has to be recomputed, but we're splitting this recomputation over many frames. This means that instead of slowing down the frame rate, instead what we see is a delay in the agent behavior, where they have to just pause for a moment while they figure out what is their new direction. This is the much more efficient way to do it, but the risk is that if the level updates too quickly, then the agents will just start standing around bewildered, never figuring out which direction they're meant to travel next. And that is why this algorithm works best when the level is changing, not too often. Now let's take this one step further for an insane test, a 300 by 300 level filled with roughly 100,000 agents. In this example, you can see a bit more clearly how the computation load is split over many frames. At the start of the scene on boot up, we have 10,000 agents that all want a new path, all at the same time. And this is simply too much to handle at once, so we do it piece by piece, and over time you can see that the agents get going, they start moving. And over time they settle into a groove where only a minority of the agents are requesting a new path in a given frame. And so from here, it moves pretty much just as quickly as the smaller example does, albeit using a lot more memory to do this. And speaking of memory, there is a failure case where this can all go wrong. To speed up the pathfinding, we are caching our results so that multiple agents can look up the same path data. And this cache has a maximum size. If this size has not been set big enough, then these agents will start fighting over space in the cache, and the result is that nobody goes anywhere, like how you're seeing in this clip. On this particular stress test example, I had to set the cache size pretty big to something like 25,000 paths in memory to avoid this from happening. But in a more normal game, more normal scenario, your cache could probably be a lot smaller. And while we're on the topic, I've made the algorithm configurable by these constants, so you can choose how much you want to spread the work out over multiple frames to best suit the game that you're making and the devices that you are targeting. Now, this ultra zoomed out example does demonstrate a second shortcoming of this algorithm, and that is that it does not find perfect paths. Instead, it finds fairly good paths, just like how a hierarchical pathfinder always does. And sometimes these rough paths look good, but if the agent is traveling through a really large distance across many sector borders, especially if they're traveling in a lot of open spaces, then these paths can start to look a bit angular and weird. And this is especially true when the sectors are wide open with few obstacles. To fix this, we got to put some smoothing on our paths. And the most simple way to do smoothing is to look ahead one tile. Basically, you move a combination of your current direction and your next direction, resulting in a sort of blended, smoother direction. And this creates fairly nice looking results in areas with lots of obstacles. Although you can see here that our agent is clipping into the walls. So if you want to stop that, you will need some kind of collision detection in your game. But in open spaces, this approach does very little to help. So we're going to need something smarter. And the approach I've gone with is line of sight checks. The basic idea is that we're going to check whether we can move in a straight line to our next portal in the portal path. And if we can, then hey, let's just move in a straight line. And then we only have to use the flow field as a backup if there are obstacles blocking our line of sight. And of course, these line of sight checks can be cached just like the paths and the flow fields can be cached, but they can also be shared between many agents. Now, since we are checking sight to the next portal node, this approach does work best in open spaces. The more obstacles you have in the way, the more likely it is you're going to end up defaulting to the flow field. But even so, the paths that you get from this are greatly improved, as you can see from this improved stress test. The line of sight checks do add extra load to the system, but not an overwhelming amount of load. And there are still places where the pathing is a little bit weird, as you can see here in some places when you're crossing sector boundaries. It can be a bit jagged and angular, but most of the time these paths look pretty good now. And there's one last important feature that I want to add. Many games don't just have walls in them, instead they have terrain. And different kinds of terrain could have different pathfinding costs. And on top of that, sometimes there are different agents that prefer different kinds of terrain. So for example, in this test case, we have one agent that strongly prefers dry land, whereas we have another agent that strongly prefers water. And so when we send these agents to the same destination point, they end up taking radically different paths through the different terrain. Now, I'd like to say that there's a quick and easy way to implement this, but it's not the case. The speed of this algorithm comes from caching and sharing data. But if two agents have different traveling types, then they can't share their data. That means that I have to duplicate the entire pathfinding data structure for every travel type in the game. So think of everything I've shown you so far: the pre-computation, the pathing, the flow fields, the line of sight checks, the recomputation when the level changes, the caching and the invalidation of caches. All of that has to be doubled to support this water guy. And if you want a third travel type, it all gets tripled instead. So this is an expensive feature. It does mainly cost memory rather than time, but even so, in my game, I am planning to have only 3 travel types. One for ground, one for water, and one for both. So there's one last topic that I've got to talk about, and it is the data-oriented tech stack. This is a set of technologies invented by Unity to let their engine run 10 times or even 100 or 1,000 times faster than it normally can, and I have made use of it for this algorithm, since, well, what's the point of making a fast algorithm if we don't implement it in a fast way? But to make this DOTS compatible, I had to jump through a lot of hoops. In particular, the types of data structures that you can use are severely limited, and since this algorithm uses a range of complex data structures, that was a tough obstacle to clear. I did get there eventually, but the resulting code is a lot more complex and long-winded and mysterious looking than I would have liked, but I guess that's just life. Secondly, I'm running a lot of this code in parallel. If we take a look at my dev computer, you can see that it has 16 cores in it, and some of those cores contain 2 virtual cores, making a total of 24. And therefore, if I can run my code in parallel on all the cores in this PC, then I can run the code 24 times faster. That's a big deal. And even a lower end PC will typically have 8 virtual cores in it, so that's still a major increase in speed. But parallel computing is not simple either. For reasons that are a bit hard to explain, it's illegal to let 2 cores write to the same data. Each core needs to have its own separate writing data, and if you then want to combine those results that come back, that has to be done on the main thread once all the parallel computing is complete. So there's a lot of steps of dividing up the data, calculating it, bringing that data back and recombining it. It gets kind of complex. I've drawn this schematic showing the order of operations that happen each frame. I won't bore you with all the technical details in this video, but if you're looking to modify my code, you will find this diagram quite helpful. Now, let's quickly cover how to integrate this into your own game. If you're not a game developer watching this, then please just bear with me a few moments. This won't take very long. First, you've got to make sure you're familiar with the basics of Unity DOTS, because it is kind of weird. Then you have to make a singleton entity with the global pathfinding data component. This is where you enter the information about your level. And once you've provided this data, the pathfinding system can begin. Then you've got to create some agents, and you do this by creating another entity for each agent that has these 4 components: a flow position, a flow goal, a flow progress, and a flow direction. You have to update the flow position each time your agent moves. This is how the Pathfinder knows where your agent currently is. And you have to update the flow goal each time your agent chooses a new destination. This is what tells the Pathfinder where your agent wants to go. So far, pretty simple. Flow progress is something that you don't have to worry about. It's all internal data that I'm using in the pathfinding system. Just make sure that the component is on the entity. And the flow direction gives you your final result. It tells you which way the Pathfinder thinks this agent should move. So let's finally get to the fun part, incorporating this into Anthill Village. Up until now, all of the levels in the game have been wide open spaces. That is because I haven't had pathfinding. But now we can have much more interesting level shapes. So I started by upgrading the level generator. So now instead of an open space, each level starts as a closed space, and I am carving out these openings into the space, creating a connected set of rooms and corridors that are reminiscent of a dungeon crawling game. This was a fairly simple change to make. In a previous video I talked about how my level generator is based around the concept of chunks. I place these chunks in a sort of big picture layout, and then each chunk is responsible for generating its own minor details. So I only had to tweak the behavior of some chunks to get this working. And this kind of level that we've got here is going to be a great playground to test the pathfinding in. But I did feel like it was starting to look quite underground, and that's not the vibe I'm going for here. This level is supposed to be above ground, outside your anthill. And so to break it up, I figured we need some grassy edges. I started with this very simple effect with some jagged green sprites around the level borders, and honestly I thought this looked really good. It has a sort of retro pixel art feeling to it. But even so, I felt like we could do a lot better here. So I built this leaf mesh. Normally I am more of a 2D game dev than a 3D dev, but I still busted out my 3D modeling skills here to make the leaf a bit volumetric and bendy. Then I arranged these leaves into circles, creating bushes. Now we've just got to place these bushes around the edges of the level. And this is actually a lot trickier than you might think, but I came up with a solution. We start by generating this heat map around the level. The further you get from the level edges, the hotter this heat map gets. Then we start looking at the hottest cells in this map in a random order, and we place bushes on these hot cells. And every time we do this, we reduce the heat of the cells around the bush that we placed, meaning the map gradually gets cooler and cooler as we place more bushes. And it's important to note here that the size of the bush we place is based on the heat of its center tile. So if a tile is not very hot, then it's going to spawn a smaller bush. And this keeps going with smaller and smaller bushes filling all of the gaps until we reach a minimum size, beyond which we stop. The end result of this is very randomly spaced bushes, but despite being random, there's still minimal overlapping between any of these bushes, and there's also increased detail closest to the level edges where the heat was lower and the bushes therefore are smaller. It's a really nice way of creating an effect that looks random but is still actually very structured. It took a lot of time and a lot of tweaking to get this looking quite the way I wanted, and everybody's feedback on the Discord server was very helpful here. A big breakthrough came when I started fading out the bushes to black, based on how distant they were from the level edges. Black is the least noticeable color. Black is basically a void. So by starting with lush green foliage at the level edges, and then fading it out quickly to black, we avoid overwhelming the player with too much detail. Okay, let's now bring the pathfinding into the game. Normally, the ants in this game follow trails, as you can see here, and these ants don't actually need any pathfinding. That's because they are, after all, already following a path. However, what happens if the ant ends up far away from its trail? For example, if I redraw the trail in a different direction. At this point, actually, the ants do need pathfinding. They need to know how they cross the gap and get to their new trail. And you can see that here. This is the first case where pathfinding is useful for the ants. Secondly, there are some cases in the game where ants move automatically without using a trail that you've placed. For example, when you put down a new building, then the ants will carry larvae to that building, where they mature into more ants. And this is done automatically, and therefore we need to calculate the path. Another example is when ants collect large resources, such as these orange slices. Before, they would take the slice back along their trail, but now I can specify a particular destination. So if you find a large piece of food, maybe it goes to a restaurant building, and if you find a large rock, then maybe it goes to a workshop building. There's a lot of possibilities here now that the ants have the option of finding a path to any destination I please. And finally, this pathfinding system is useful for more than just the ants. In fact, it's very useful for all of the other creatures I want to put in the game. As a placeholder here, I've put in Crow Camel, who's a character from my last game, Patch Quest. I chose him because he eats bugs and therefore he seemed like a natural fit. This is just a placeholder. I will create unique creatures for this game in due time, but for now this demonstrates how pathfinding is good for more than just the ants. It's a tool that has many different uses, and it's really going to expand the gameplay that I can put into this game. So let's now think about the next steps. What's in the next dev cycle? In the last video, I talked about adding big game hunting to the game, that is, hunting large creatures such as that crow camel. I think that's a really good starting point, and we'll start reintroducing combat mechanics into the game. And from there, I might start looking into aphid ranching or perhaps beekeeping. These are both going to involve creatures, but in a more complex way than big game hunting. And I probably won't have time for both of them, so if you have a preference, let me know in the comment section. And we do have one last important thing to mention. Since the last video, we have gone from 0 wishlists to 1,629 wishlists, which is amazing. A really good start for a game that is so early in development. And these wishlists really do make a difference. In fact, they're probably the single biggest factor that will help determine how well this game does on launch. We live in an algorithm-driven world, and Steam is looking at this data and stroking its beard and twizzling its mustache and deciding what games deserve attention. So if you want to help support me as a game developer, there's a link below where you can wishlist the game. That's all for now, and as always, thanks for watching.